Remember our discussion of uncertainty? We said that uncertainty could enter into game theory in any of three different ways. One of them we explored thoroughly. A player may use chance in determining which strategy to play. The result was a mixed strategy. Today, I want to look at the other two possibilities. Maybe your game includes random events. Or maybe you're not exactly sure what game it is that you're playing. This is an unfortunate but a real possibility. Games have players, strategies, and payoffs, and we generally assume that these things are common knowledge. But what if they aren't? You might not know exactly what strategies another player is capable of. Can they really steal my best customer? Or you might not know what another player's payoffs are. What is this promotion really worth to me? A game that includes either of these two types of uncertainty is called a game of incomplete information. It means basically that you have questions about the structure of the game. But even if you have complete information, there's still another source of uncertainty. Secrets. Insider knowledge. You may know that a new zoning law is being passed. I may not. I may be interviewing for a change in jobs, but I haven't told you. When one player knows something that another player doesn't, it's generally called asymmetric information. Asymmetric information arises when one player knows something about the history of the game, either a random event or a player's decision, that the other player doesn't. Asymmetric information is a special case of imperfect information. Imperfect information comes up any time that a player doesn't know some aspect of the game's history at the time that that player makes a decision. It turns out that acts of nature, chance events, don't cause much trouble in a game as long as everybody knows the same thing about the event. If we all know what happened, no problem. We can approach it with the expected value approach that we've been developing over the last several lectures. This is also the case if no one knows about the outcome of the event until later. In game theory, you can just delay the appearance of the chance event until later in the problem. For example, suppose that we're bidding on a box which contains either $1 or $100. The amount of money that's in the box could be determined before the bidding gets started, but game theoretically, we could treat it in the same way as saying that the amount that's in the box isn't decided until the last moment before the box is unsealed. It really doesn't matter which way we model this. But how about when you have questions about the structure of the game itself? That is, when you're dealing with a game of incomplete information. The answer to that difficult question was found by John Harsanyi, who got a Nobel Prize for being so clever. He introduced the Harsanyi transformation. It allows any game of incomplete information to be turned into a game of imperfect information. The basic idea behind the Harsanyi transformation builds on the idea of types. You don't know exactly what your other player's abilities or payoffs are? Then create a spectrum of possible other players, types, and assign a probability to each one of them. Then figure out how you would play against that variety of actual players. The likely types are going to get higher probabilities than the unlikely ones. A solvent IBM is going to be more likely than an insolvent one. And when you've got this worked out, you just start the game tree with a chance node. The chance node randomly determines which type you're dealing with, and then you play the game. Your optimal strategy is going to be the one that does best in the sense of expected value against this entire spectrum of opponents. Usually, each player knows his or her own type, but may not know the type of another. In that case, the Harsanyi transformation turns a game of incomplete information into a game of asymmetric information. It's like you're dealing with a player who has a secret. So, how do we handle a game of asymmetric information? Good question. I'm going to address it by presenting a classic example of how a little asymmetric information can have far-reaching consequences. It's generally called the market for lemons. It was presented in a paper by an assistant economics professor named George Akerlof back in the 1960s. Akerlof had trouble getting this paper published, which is funny because when people eventually caught on to what he was saying, he ended up being another Nobel Prize winner in economics. Let's start out by assuming that there are two kinds of used cars: bad ones, lemons, and good ones, peaches. Peaches are obviously the better cars, but you'd be willing to buy a lemon if the price were right. Let's say you're willing to pay up to $6,000 for a peach, but only $2,000 for a lemon. I'm selling the cars. To me, a peach is worth $4,999, and a lemon's worth $999. For either type of car, then, the car is worth $1,001 more to you than it is to me. So it looks like we should be able to make a deal on either kind of car. Okay, you come to my lot, you pick your favorite car, and we're going to assume that the car that you picked is equally likely to be a peach or a lemon. You make an offer. For simplicity, let's frame this as an ultimatum game. You set the price, and I take it or leave it. I'll accept any offer which is anything over what I find the car to be worth. I'm also going to make one more assumption, one which I'm later going to change. Let's assume that both you and I can tell the value of the car. We can tell whether it's a peach or a lemon. Then this game involves chance, but not imperfect information. When we make decisions, we know the entire history of the game. The tree for this sequential game would look like this. Notice that it starts with a move by nature, determining whether the car is a lemon or a peach. Technically, you could offer any price you wanted for the cars, but I'll never accept an offer below $1,000, and I'll always accept $5,000 for any car on the lot. So I put these two on the tree, and the midpoint between the two prices, $3,000. Replace the $3,000 with a different number if you want between the upper and lower limits. You'll get the same results. I'm just trying to keep things clear. Okay, so what happens? The game starts with a chance node played by nature. Half the time, we go to the upper branch, where the car is a lemon, and half the time to the lower branch, where the car is a peach. You can see the little 1/2 next to each branch, indicating those probabilities. Since this is a game of perfect information, we roll it back exactly the same way that we did with our earlier trees. I'll stop when I get to the chance node. Take a look. What does the tree tell us? It's no surprise, really. If the car is a lemon, you offer me $1,000, and I take it. You make $1,000, and I make $1. If the car is a peach, you offer me $5,000, and again, I take it. You make $1,000, and I make $1. That chance note at the beginning really didn't have a big effect on our analysis. There are really two different games of perfect information being played here. One for a lemon, one for a peach, each being played half the time. That means that our average payoffs are half of our lemon payoffs plus half of our peach payoffs. Probability times payoff added up over all the cases, remember? By coincidence, you make $1,000 either way, so your average payoff is $1,000, and I make $1 either way, so my average payoff is $1. You were on the right side of the ultimatum game. But this analysis assumes that both of us can tell a lemon from a peach. They look identical on the dealership lot. How about if neither of us can tell the difference? Can we model this? Yeah, easily. We now have a piece of information that's unknown to everyone until the deal comes to a close. That means it can have no effect on the play of the game until we get to payoffs. The tree now looks like this. We don't find out what the car is until the very end of the deal. We're going to roll this back by computing the expected payoffs at each of those chance nodes. For example, at the top chance node, we see what happens when you buy the car for $1,000. Half of the time you make $1,000, half of the time you make $5,000. Probability times payoff added up over all the cases gives half of $1,000 plus half of $5,000. That's $3,000. We'll carry on this way and roll back the whole tree. It's actually pretty easy to understand. The car we're talking about has a 50% chance of being a peach and a 50% chance of being a lemon. That means its expected value to you is your average of a peach or a lemon, which is $4,000. Its average value to me is halfway between my values for a peach and a lemon, $29.99. So I'm not going to accept an offer of less than $3,000, but I will accept $3,000 or more. You knowing that, you offer $3,000 and we close the deal. Half the time you get a peach. Half the time you get a lemon. And on the average, that means that you're going to make $1,000. Similarly, on average, I'll again make $1. Well, neither of these cases that we looked at so far were very hard to handle. That's because both of us had the same information. But things aren't always like this. And this is where Akerlof's paper comes in. What if I, the car dealer, can spot a lemon, but you can't? I know the cars better than you. We now have a game of asymmetric information. I know something you don't when we're making our decisions. And that does change things. We can still represent the game on a game tree, but it's got something new. See those dotted lines between the two red nodes? They mean that those two nodes are in the same information set. It's like having two identical rooms in your house. If you woke up in one, there'd be no way for you to know that you weren't in the other. In the same way, there's no way that a player can distinguish between one node in an information set and any other. So when you reach your decision node, the tree knows whether the car is a lemon or not, but you don't. How about me? Take a look at the tree. You can see that each one of my blue nodes is its own information set. I know where I am. I know whether the car is a lemon, and I know how much you offered. I know everything. So what happens in this game? Well, in the second game, you didn't know whether it was a peach or a lemon, so you just went with the average value of a peach and a lemon. That was $4,000 to you and $29.99 to me. So how about doing what you did last time? Offer me $3,000. Do you see the problem? You may not know if it's a lemon or a peach, but I do. You offer me $3,000. If I know the car to be a lemon, I'll be more than happy to sell it to you, but you'll be sorry that you bought it. You just paid $3,000 for a car that you think's only worth $2,000. Well, that happened in the second game too. Sometimes you overpay for a lemon, and sometimes you get lucky on a peach. But you don't. Not anymore. I can tell whether the car is a lemon or a peach. If you picked a peach, I'll refuse your $3,000 offer. A peach is worth almost $5,000 to me. Do you see what happened? I'll only agree to your $3,000 offer if it's on a car that you wouldn't be willing to pay $3,000 for. We can reason our way through all the possibilities. If you offer me less than $1,000, I won't sell you any car. If you offer me between $1,000 and $49.99, I'll sell you a lemon, but not a peach. A lemon's worth $2,000 to you, so we've got some room between $1,000 and $2,000 to make a deal on a lemon. If you offer me $5,000 or more, I'll sell you any car on the lot. The trouble is, half of the time that car is going to be a lemon. We've already worked out that if a car has a 50-50 shot at being a lemon or being a peach, its expected value to you is $3,000. So you're not going to offer enough to me to sell you a peach. Ever. There's a market for lemons which are worth $1,001 more to you than they are to me. There should be a market for peaches for the same reason. But because of asymmetric information, this mutually beneficial trade will never take place. That's the reason that Akerlof got the Nobel Prize, because he showed this problem of asymmetric information applied to a lot more than used cars. It crops up all over the place. Think of health insurance. There's been a lot of debate recently over how the health crisis in America should be handled. Should coverage be mandated? Let's look at the question from a game theoretic perspective in terms of asymmetric information. Each American is going to need some level of healthcare expenses for the coming year. I'll record this information, but do it in an unusual way. For each American, I'll take a grain of sand. I've got a wooden plank here with the dollars marked on it at different points, and I'll take your grain of sand and put it with whatever your healthcare costs are. If your costs are $20,000, I'll put your grain of sand over the $20,000 mark. I'm going to do this for everybody. There's a 60. There's a 160. When I'm done with everybody in America, I'll have a big pile of sand that might look like this. In this fictionalized example, nobody had medical bills higher than $160,000, the upper end of my plank. This picture's only meant to be suggestive. If I drew it with the real numbers, it'd be much harder to see all the sand. Anyway, as you can see, we have a lot of sand on the plank near a healthcare cost of 0. You can also see that there's a small pile in the center of the plank near $80,000, and some grains extending all the way up to the high end. A picture like this is usually called the probability distribution of healthcare costs. Well, when you want to find the expected value or the average of a probability distribution, you generally use calculus. But the result can be thought of much more easily. Imagine that we're going to make a teeter-totter out of my plank. I have to find the point where the two sides just balance. I've drawn a very skinny plank here because it's really the sand that I want to have balancing, so assume that the weight of the plank itself is negligible. You can show that the average value, the expected value of this distribution, is the point where the seesaw balances. Well, if you've ever had a brother or sister who's considerably heavier or lighter than you when you were a kid, then you know how to make the thing balance. The larger kid sits near the center of the seesaw, and the lighter kid sits way out toward the end. I've shown the balance point of my distribution with a red triangle. This balance point, or fulcrum, falls at about 10,000 on my plank, which means that the average healthcare costs for Americans is about $10,000 in this example. Okay, time to buy healthcare coverage. How much does it cost? Well, you're one of the grains of sand on this plank, and the average cost per grain is $10,000. So that's a reasonable amount for you to pay. If you don't know which grain, you are. But people often know more about their general health than the insurance company does. This creates an information asymmetry. You won't be able to exactly predict what your healthcare costs are going to be, but you'll probably come close. You might miss by a lot, but it doesn't happen much. I'm going to keep the analysis simple and pretend that people are able to exactly predict their healthcare costs. It won't change the argument in any substantive way. To cover expenses, the healthcare coverage is going to have to cost $10,000. That's where the fulcrum of our teeter-totter is. So, who buys insurance? Well, you're not going to buy it if you're to the left of the fulcrum. People on the left of the red triangle are paying $10,000 for less than $10,000 worth of healthcare. They're not going to pay. So get rid of those people from the picture. Great. Or is it? The heavy kid just got off with a teeter-totter. Obviously, the remaining sand doesn't balance at the red fulcrum anymore. We're going to have to move the balance point. Quite a lot. There. That'll do it. The average healthcare cost of the people still riding is $75,000. So that's what we have to charge for the system to break even. $75,000? That's a lot of money. And the people whose costs are expected to be less than $75,000 aren't going to want to pay it. They'll drop off, getting off of the teeter-totter, and all that sand leaves, and the fulcrum has to move again. I won't draw you any more pictures, and I'm sure that you don't need them. What happens is simple enough. Whoever's on the left side of the teeter-totter gets off, unbalancing it. The fulcrum moves to the right to rebalance, and this procedure keeps on going until eventually healthcare costs $160,000 and no one buys it. This is why universal healthcare plans need to be universal. Otherwise, information asymmetry destroys the market. And it's not just cars and insurance. Think about employment. The applicant for the job knows whether or not he's competent and intends to work hard, but the interviewer doesn't. So some of the employees are going to turn out to be lemons and some will turn out to be peaches. The employer offers a lower salary. This salary is a weighted average of what you'd pay a peach and what you'd pay a lemon, depending on their relative proportions in the market. But that average is going to underpay a peach. So peaches are going to start to drop out of this market and find something else to do. That means the actual pool of participants has more lemons than you previously thought. That means that the blended salary that the employer is paying is now too high. So they lower it, which discourages more peaches from being in the market, which means that there's more lemons, which means that the salary gets lowered again, and as you can see, we've got the same problem. It's not that the employer would not be willing to pay more for a peach. She would. It's simply that the inability to identify a peach destroys the market for peaches. In some ways, it can get worse than this. We've assumed so far that there are peaches and there are lemons. But what if the very act of making an offer can turn a peach into a lemon? This is a very real problem, and it comes up a lot. The general term used for this situation is moral hazard. The problem comes up when a party doesn't bear the full costs for his or her choices. When this is the case, the party is likely to be less careful in making those choices. I mentioned in my first lecture that the question of why American League pitchers threw more beanballs than National League pitchers. And they do, about 15% more. And the reason is moral hazard. I'll wait a few seconds before explaining what I mean by this, for those of you who are baseball fans and would like to figure it out on your own. In the meantime, here are a couple more examples. I'm generally not going to park my expensive car in a poorly lit back street. Too much chance of vandalism. But I'd be more likely to do so if I knew my insurance company would cover the cost of any damage. Moral hazard. When my doctor says that he thinks that he should have some more tests run, I generally don't ask how much they cost. I've already paid my co-payment, and the insurance company will do the rest. This means the medical community can charge more for those tests than I'd personally be willing to pay. Moral hazard. Mortgage companies are more likely to make high-risk loans if they know that if things go badly, the government will bail them out. In fact, any time that a government considers a bailout, the risk of moral hazard is really quite real. All of these examples involve asymmetric information, and moral hazard arises when the party with more information acts in a way that would be deemed inappropriate by the party with less information, if they knew what was going on. Okay, the beanball question. Why do American League pitchers throw more beanballs? The reason is the designated hitter rule. In the American League, pitchers don't bat. Instead, another player, a designated hitter, stands in for them. In the National League, there are no designated hitters. Pitchers have to bat. This means that if you're a pitcher and you bean a batter on the other side with your pitch, in the National League, you're going to be in the batter's box yourself in a little bit. And after your little trick, their pitcher might have a 90-mile-an-hour fastball with your name on it. American League pitchers face no such threat. In games between the National and American Leagues, the pattern holds. Sometimes these games have a designated hitter. Sometimes they don't. In games with a designated hitter, where the pitcher doesn't have to bat, more batters get hit. Here's another one. In the first lecture, I promised to revisit the question of why car insurance costs more in Philadelphia than it does in Pittsburgh. And it does, almost twice as much. Clearly, both cities are in the same state, Pennsylvania, so it's not state law. Nor is it rates of vandalism. They're actually lower in Philadelphia. It's a matter of different equilibria, driven by an issue of moral hazard. Less people in Philadelphia have auto insurance, even though it's mandated. This means that more accidents involve uninsured drivers. If you have an accident with an uninsured driver, that means that your insurance company is going to have to pay for the damages. This costs the company money, so they raise your insurance rates. With higher rates, less people can afford car insurance, and the cycle perpetuates. The moral hazard aspect of this comes in with the fact that the uninsured are not responsible for the extra damage, or risk of damage, that they introduce into driving. And as a consequence, anybody who buys car insurance in Philadelphia is likely to be unhappy with the prices they have to pay. The effects can be quite dramatic. Okay, I want to end today's lecture by returning to the idea of information sets and decision trees. You'll remember how in the used car problem you had two nodes in the same information set, since you didn't know whether the car that you were buying was a lemon or a peach. Since your decision came immediately after that chance node, we were still in a pretty good shape for being able to analyze the rest of the game. You knew there was a 50% chance that you were in the lemon branch and a 50% chance that you were in the peach. The situation can get more complicated, a lot more complicated than this. I want to give you an example that's only slightly more complicated. Here's a very simplified version of poker, which I call tiny poker. To begin with, I put $40 in the kitty. The kitty is simply a pool of money. If one player wins, that player gets all the money in the kitty. If we tie, the money in the kitty is split evenly. So I put $40 in to begin the game, and you have to put in $70. That's $110 total. You have to put in more because, as it turns out in this game, there's a first mover disadvantage, and I'm going to be going first. Okay, we put in our initial cash, and after that, we're dealt a single card from a deck of only 3 cards. The 3 cards are labeled 1, 1, and 2. There are 3 equally likely deals, of course, because we both get 1 card. Either you get the 2, I get the 2, or nobody gets the 2. Each happens 1/3 of the time. We each see our own card, but no one sees the card of the other player. If neither of us quits the game, at the end, whoever has the 2 wins and gets all the money. And if neither of us has the 2, we split the pot right down the middle. But someone might quit before this happens. After I look at my card, I can decide whether to quit, to fold, or to continue. If I want to keep on going, I have to add $70 more to the kitty. Look at the tree. You'll see that my top 2 nodes are in the same information set. Those 2 nodes correspond to my looking at my hand and seeing a 1. I don't know where the 2 is. Maybe you have it. Maybe no one does. I think it's pretty clear from the problem that if I have a 1, then half the time you have the 2, and half the time you don't. That's the 1 card left that wasn't in the deal. So I can keep going or fold. If I fold, I lose, and you get my $40 that was already on the table. If I keep going, I have to pay another $70. Then it's your turn. Like me, you can decide to fold if you want. If you do, I win the kitty, so that means I get your $70. I get my money back too, but that's not winning anything. On the other hand, you may decide to keep on going after you look at your hand, and if you do, you have to pay an additional $30. Look at your information sets on the tree. 2 nodes tied together are where you have a 1 and didn't quit. Maybe I have the 2, maybe no one does. You don't know. If you pay $30 to stay in the game, then we both reveal our hands. Whoever has the 2 wins. Since I've put in 110 total and you only put in 100, a win is a little better for you than it is for me. If we both have a 1, we both tie. Again, because I put in $10 more than you did, this actually means that you make $5 off of me in this case. Well, the tree makes pretty good sense once you look at it carefully. The thing that's tricky is to figure out what to do. And things here are actually pretty tangled. Suppose I look at my hand and see I have a 1. I know there's a 50-50 chance that you have the 2. That's not too hard. It's easy to see that I should continue with a 2 since I can't lose, but how about if I have a 1? With a 1, I'm guaranteed to lose. Unless you quit. Which you might, if you have a 1. So maybe I should bluff with a 1. How often should I do it? Well, that depends on how often you're going to quit with a 1. But whether I fold with a 1 depends on whether you fold with a 1 depends on how likely you think it is that when I keep on playing, I have a 2. And that depends on how often I bluff. So how often I bluff depends on how often you keep playing with a 1, which in turn depends on how often I bluff. This sound familiar? It should. It's the same kind of reasoning we went through with simultaneous games. And believe it or not, it's simultaneous games that are going to get us out of this mess. Every sequential game can be expressed as a simultaneous game. Saying it another way, if you can express it in a game tree, you can express it in a matrix. We're going to see how our little poker game here can be rewritten to be written as a game tree. As a matrix. We're going to be also seeing how we can use the ideas of information signaling and imperfect information to solve this problem. Signaling combines the notion of credibility from the last lecture with the idea of imperfect information from this one. Basically, if I know something that you don't, how can I tell it to you and get you to believe me?